Hello everybody and welcome to this Key Stage 3 Science video. What I'm going to do in this video is a bit of a review of some Key Stage 3 chemistry questions, and we'll be focusing on acids and alkalis, particles and mixtures. Now the first time I show a question on the screen it won't have any answers on it, so if you haven't seen these questions before you can pause the video and have a go at them before I do a walkthrough of how to think about them and how to answer them. And on that note, my thoughts will be written in blue as well as spoken, of course, and the actual answers, the things that will get you credit, they will be in green. This first question is about some reactions of copper, and the question says that a school student heated some copper powder until it went black. And our first question is to give the name of the black substance formed when copper reacts with oxygen. Now, when any substance reacts with oxygen, the chemical turns into an oxide. So if we had any element and we heat it with oxygen, it will make something oxide. And that something will depend on what the element is. So a piece of copper will become copper oxide. And the reason is that the oxygen reacts with the element and forms a layer around the outside of the copper. So a black coating of copper oxide will appear on the copper. Second part of the question, Ellen added the black substance to some dilute sulfuric acid, so the copper oxide has been added to dilute sulfuric acid. The black substance reacted to form a blue solution of copper sulfate. What type of substance is copper sulfate? Acid, compound, element or mixture? So it has formed as a result of a reaction with sulfuric acid. So acid seems unlikely. Now a compound is two or more elements chemically bonded together. And so that seems very likely to be the right answer. So two or more elements chemically bonded. A mixture is something like sand and gravel or sand and clay. And so a mixture is two things in the same place and they're not chemically bonded, but they are together. And so that's not going to be right. And an element only contains one type of atom. And in copper sulfate, we actually have three types of atom. We have copper, we have sulfur, and we have oxygen. So compound is the correct answer there for our mark. Ellen takes her copper sulfate solution and she pours it into a dish. And this is the dish here. She left the dish in a room at 21 degrees C for 2 days. What two changes would Ellen notice 2 days later? Now, this type of reaction is crystallization. And what is going to happen is our solution, and you can always do this for any solution, so you can have salt solution, and the water can evaporate. So the water will leave the solution, and so that will be one change that you'll notice, is that there will be less solution or less water or less liquid. And then the second change is that around the edge of the container you'll start to get solid crystals of copper sulfate, and if enough of that water goes, or maybe all the water goes, you'll see it being totally sort of full of crystals. So the observation, what will she observe? She will observe crystals forming, and that is solid copper sulfate. And then finally she pours 20 centimeters cubed of the same copper sulfate into another dish, and she puts a lid on that dish, and again she leaves it for 2 days. And so after 2 days the contents of dish B look different to the contents of dish A. Give one difference you would observe and explain how the lid caused the difference. Well, it's totally tied to what we've just said, really. Those are the only two things that she's likely to observe. And adding the lid stops the water that has evaporated from the solution from leaving. And so what will happen is it will condense on the lid, and then it will probably dribble back down into the solution. Some of it will escape through the edges, and so the water level might go down, but certainly if we take these observations one at a time, less solution would form, less water would be there. Well, for here, let's just take that and use that exactly how it is. There would be more solution would be left over. And in terms of the crystals forming, there wouldn't be so many crystals, so we can just write fewer crystals. And so either of those is absolutely fine. Now let's be careful with the question, because the question said give one difference, and what I've done here is I've given two. So we can either say this first one or we can say the second one. We don't need to say both, but what we do need to do is explain how the lid causes the difference. So there'd be more solution because the lid prevents evaporation, and so that would actually get us both of the 2 marks. And then the second answer, there would be fewer crystals, and that would be because less water evaporated. And so they're both quite closely linked together, but you only needed to say one kind of pair of answers. More solution because lid prevents evaporation, or fewer crystals because less water evaporated. This question is about separating mixtures, and there is a student who's taken some different coloured oils, yellow, green and blue, and she's tried to dissolve them in different solvents. Now a solvent is something that is able to dissolve a different type of substance called a solute, usually a solid solute, but it could be a liquid as well. And so we've got this on the left here, a solute dissolves a solvent to make a solution. That's something that's really important that you know. And I know it's confusing because there's lots of words that all begin with sol, and I'm actually going to give you another 2 that sound similar. The first of the 2 is soluble, and that means that something will dissolve, and then the follow-up word is insoluble, and that means that a thing won't dissolve. And so what we're going to do now is we're going to take a look at the results table and decide if the paints are soluble or not. So the yellow paint, we've got yellow pieces are left in the water, and so that's insoluble, it didn't dissolve. And then it's the same again in the ethanol, it didn't dissolve. But there's a clear yellow liquid in propanone, and so that means it has dissolved. The blue paint has got pieces left in the water, so that's insoluble. But it's soluble in the ethanol because it's a clear blue liquid, and soluble in the propanone as well. And then last of all, the green paint, we have got green pieces left, so insoluble in water, and then there's a clear blue liquid, but yellow pieces are left. So that's a question mark there, we'll come back to that one. And then propanone, we've got a clear green liquid, so that is soluble. So which solvent does not dissolve the blue paint? And so we're looking at the middle column, and the answer is water. Water, in fact, didn't dissolve any of them. She then uses chromatography to investigate the paints. And what we have in chromatography is we have the piece of chromatography paper, which has got a pencil line marked on it, and 3 spots of the different coloured paints will be placed upon it. And then the solvent rises up the paper, and what happens is the different coloured paints will rise different distances up the paper as they dissolve the oil and carry it up the piece of chromatography paper. Now the crucial thing here though is that the solvent, if it's going to move the chemicals, it must dissolve them. And so what we need to do is we need to look back at our results table that we've been given, and the question says only one of the solvents will make all 3 paints move up the chromatography paper. Which one is it? And the answer is propanone. And the reason that propanone is the answer is that it was the one that dissolved all 3 of the paints. In every single case for propanone, we got a clear liquid, clear liquid, clear liquid. In other words, no bits left that hadn't been dissolved. And then there's a follow-up part to the question that the scientist is investigating the paint used in 3 different oil paintings. And so she takes a tiny bit of the yellow and the blue and the green paint from each picture, and she uses chromatography to compare them. And here are her results. She's got the 3 pictures. Picture 1, which was painted in 1993, picture 2 in 1625, and picture 3 painted at a time that is not known. And then the question says, which of the paints in 1993 contains only one substance? And so what you have to do here is we look at the green paint, and we can see that there are 3 different spots in it. So that green paint actually had 3 different substances. And the blue has got 2 spots. And so the blue contained 2 substances. And it was the yellow that only contained 1 substance because it's risen up the chromatography paper and we've only been left with 1 spot. And then the scientists decided that paper 3 is probably recent and not from around 1625. Look at the chromatography results for the 3 pictures and explain how the scientist was able to decide this. Now, this is probably the hardest question so far, really, because what we have to do is we have to compare how high each of the spots travel and look for similarities. Now, I know I said blue for thoughts, but I want to change it to a different colour so it stands out. And so let's look at the yellow pigment. The yellow pigment in this unknown time matches precisely with the yellow pigment from 1993. And so that's some really strong evidence that there is a similar date for picture 3. And then if we have a look at the blue substance, there's 2 spots here in in the unknown date. And then if we track that along, that matches perfectly with the 2 spots from 1993. And then if we track the 3 green spots in the unknown period, again, tracking to the side, it matches perfectly with the 3 spots from 1993. So that means that probably the painter used similar oils in the unknown date to this other painter presumably used in the 1993 date. And then if we contrast that with the 1625 paint, there's a little colour here that's green, but it doesn't match. There's another colour here that doesn't match. And there's another colour here that's yellow, and that doesn't match. So there is some similarity. The 3 that I haven't coloured in, they match, but the 3 that I have coloured in don't match. And so that's how you would need to answer this question. The question is only worth 2 marks, and so you don't have to write loads. I would say you need to give 1 piece of evidence why picture 3 is similar to picture 1, and 1 piece of evidence why picture 3 is different to picture 2. And so here are some options of things that you could pick. There's actually 3 similarities and 3 differences that we've listed. Okay, this question is about particles, and it's particles of gas inside a piston which is moving to the right. So the piston is moving this way. And we've been given a key to our gas, and the gas contains 1 atom of nitrogen and 1 atom of oxygen combined together. So how can we tell that this substance is a gas? Let's just dive in with the answers on this one. And it's a gas because the particles or the molecules are far apart. And we know that gases, they go around, they're really far apart. And it's only gases that can be compressed. And in fact, you could say either of those things to get that first mark, but you don't need to say both. How can you tell from the diagram that the gas is pure? Now, pure means that there is only 1 substance present. And that's what we've got here. There's only 1 type of substance. And I've just written underneath actually 3 alternative words that you could use instead of the word substance. So you could say substance, or you could say compound, or you could say particle. You don't need to say all 3. That / means either of these is equally good. And then in this second question, we've got a piston that has moved to the right. And the question says, how can we tell that the pressure of the gas has increased? And there's really 3 things that you could say here, because pressure is a measure of the distance between particles. And so the distance between the particles has got smaller, or you could just simply say the particles are closer together, or you could comment on the fact that it looks like there are more particles hitting the sides of the container. And so that's something else that indicates a higher pressure. That's actually literally what pressure is. Particles inside a container colliding with the sides. Do remember though, this is only 1 mark, so you don't need to say all 3 of those things, just 1 of them. Okay, we're still looking at pistons here, and so in diagram C, it shows what's happened after the gas has been compressed. And the question says, how can you tell that a chemical reaction has happened when the gas was compressed? Now, a chemical reaction is when the atoms change how they are bonded, and new compounds form as a result of it. And that's actually the answer to this question, that new compounds have formed. And we can tell that new compounds have formed because originally in the diagram we had 1 black circle and 1 empty circle. And now though, we don't have that. Well, we have 1 of them, but we also have a number of other things here. We've got 2 of these black circles with 1 white, and then we've got another one of those over here. So if we just circle them in a different colour, so we've got, that's another one. And then we've also got a third type of compound now, which has got 2 white circles and 1 black. So we've actually got 3 different types of compound. So definitely the atoms have changed how they are bonded together. The mass of the gas in both diagrams B and diagram C was 0.3 grams. Why did the mass of the gas not change when it was compressed? Now, you could almost turn this on its head and think, why would it change? And the only reason that a mass would change is if you had a container and more stuff was added to it, or we had a container and stuff left. Now, unless that's happening, the mass won't change. And that's the answer to this question, that the atoms have not been gained or lost, and so it can't possibly have changed. Or you could just simply say that we've got the same number of atoms. If you took the time to count up the number of black circles and the number of white circles on all the pictures, they're all the same throughout. Yes, they've changed how they're joined together in diagram C, but there are the same number of them, and so that's the answer. This next question is about chemical formula, and the chemical formula, or formulae when we're talking about more than one of them, that you'll be most familiar with are things like H2O, which is water, and that means there are 2 hydrogen and there is only 1 oxygen. When it's a 1, we don't write it. CO2, which is where there's 1 carbon and 2 oxygen. That little 2 will be the number that belongs to the element that's just gone before, or simply the gas O2 for oxygen, meaning 2 oxygen atoms joined together. And if we were drawing it using this key, it would look like this. So to move over to here, we've got 1 nitrogen and we've got 1 oxygen, so the formula we simply write NO. In the second one, this time we've got 2 of the black circles, which are the nitrogen, and so you write N2O. So it's very similar to H2O, except we've got 2 nitrogen instead of 2 oxygen. And then last of all, we've got 1 nitrogen here and we've got 2 oxygen, so it's NO2. So that's really similar to CO2, except it's an N instead of a C this time. Now, the absolute thing that you must remember is, if I just write O2 again, it's a little 2 down on the line. That is the way to write it. It is definitely not O with a 2 up in the air or O with a big 2. Both of those are wrong, and please don't ever do that one. And last of all, what is the name of the substance with 1 black circle and 1 white circle? Now, the black circle is nitrogen and the white circle is oxygen. Now, when you're naming compounds that have got 2 elements in it, instead of it being nitrogen oxygen, you don't just run the 2 elements all together. The name ends in "ide", and it's nitrogen oxide is the name for this chemical. This final question is about acids and alkalis. Now, someone has taken 10 cm cubed of an acid solution and they've added alkali to it a little bit at a time. So they've got some alkali and they've added a bit of it in here. And what they've done is they have recorded what happened to the meter reading on a pH meter, and that's this piece of equipment here, currently reading 5.5 on its scale. We can see that here, so it's presumably representing this bit of the diagram. And so what's happened is they measured the pH at the beginning, so this is when no alkali has been added, so that's the start, and the pH was 5 at the start, and then they added 2 centimeters cubed of alkali, and they measured the new pH, and then they added another 2, measured the new pH, then they added another 2, measured the new pH, etc., all the way along until they'd added 20 cubic centimetres of alkali, measuring the pH each time. And what you've been asked to do in this question is to draw your graph and then just answer one question about your graph. Now, when you're plotting graphs, you need to know the rules of results tables. Now, results tables always have the thing that is being changed, that's the independent variable, that needs to go on your x-axis. And the x-axis is the one that goes across because an x is across. And the result that gets measured is called the dependent variable, and that must always go on the y-axis, and the y-axis is the one that goes upwards because upwards is where we find the sky, and y goes to the sky. That's how people like to remember that. So, looking at the marks, they're really explicit in how they're going to give you the marks. You're going to get 1 mark for labelling your axes. You're going to get some marks for plotting the points. That's likely to be 2 because the total mark is 4. and you're going to get 1 mark for drawing your smooth curve. So that's the mark spread that we usually get, but I would say that because this is quite an awkward graph to plot, I think on this occasion you're only going to get 1 point for plotting all of these correct points, and you're going to get another mark for a good scale on both of your axes. So I think it will be labelling your axes, 1 mark, plotting your points, a second one, good scale, a third one, and then a smooth curve, the fourth one. So you should literally rewrite the titles for those table headings on your correct axes for your graph. And don't forget, when you are labelling your axes, that you must include the units as well. That will cost you the mark if you don't. And then the next part of this is you need to draw an accurate scale. Now the good news is they've given you the graph paper, and they've given you the right amount of graph paper, and you must try and use as much of it as you possibly can. So the volume of alkali added at the beginning is 0, and that goes up to 20. And so if we work up in twos, 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. So that fits perfectly on our x-axis. Now you might be tempted to start your y-axis at 0, but you don't really need to, and you certainly won't get any extra marks for starting it at 0. So what I suggest is that we've got enough space to go up in halves. So I suggest we start at 5 and we go up in halves. Remember, we need to go up as far as 9, and so here we get to 8.5 and we get to 9, and that fits almost perfectly as well. So that would be my suggestion on the scale. And then we need to plot our points. So our first point is at 0 alkali, and a pH of 5. And so we put a little cross, do this in pencil for your own work, at 0 and then 5. And then the next reading is for 2 cm cubed has been added, and that is still 5. So 2 on the x-axis and 5 on the y-axis. And so we plot it like this. And then the next one is for 4 on the x-axis and 5 on the y-axis. And so that is still the same line along here. And then the next one is for 6 on the x-axis and 5.5 on the y-axis. So we're changing a little bit. So we've hit 6 on the x-axis, and 5.5 means we're going up 5 little squares. Each little square is 0.1. And then 8 has gone up to 6. And then 10 has gone up to 7, and then 12 has gone up to 8, 14 is 8.5, 16 is 9, and then 18 is 9, and then 20 is 9 as well. Those points that I've just drawn actually aren't in a very good line for 9. Let's just redraw those just a little bit more carefully. There we go. So it's important to do this in pencil, because if you make a mistake, you can rub it out and do it again. And so now we've plotted our points, we've got our third mark, and the final task is to draw a smooth curve. And so a smooth curve, you might need to move your piece of paper around, or certainly we might need to work out where we're going to need to turn our curve. So first of all, I'm in blue, so this is thoughts, not marks. This bit looks flat, and so that's going to be a flat horizontal line going from left to right, like this. And then, at the very end, this bit also looks like it's flat. So what we're going to get, and I'll do this in blue before we can get the actual general idea here, is it's going to be flat, it's going to go up, and then it's going to be flat. But it needs to be a decent curve all the way. So, we've started flat, we're going to curve, and then we're going to go upwards. Now, the curve gets steeper and steeper, so try not to stop and start too many times, because if you get sort of what's called a feathered line of best fit, then that will cost you. So the line that I've drawn here is good. I have actually missed a bit of my line here, so I've kind of moved away from it. This one that I've done again is a bit better. I like that one more. So again, another reason why you would do your best fit line in pencil. And if you end up, when you rub out a line that you didn't like, and you end up having to go back over your points, don't forget to really make it clear that you have plotted your points correctly, and go over them again like I've just done there, just to show that I do want all of those marks. So that's the curve plotted and all our marks have been awarded. And last of all, it says look at the graph. What would the likely pH of the solution be if the solution added a further 2 centimetres cubed of alkali? And so we need to take our line and kind of continue it along. So at 20, we had a pH of 9, and it looks like it's flat. We've already said it looks flat. And so we could expect that pattern to continue. And so therefore the answer, and the only acceptable answer, is 9, or I suppose 9.0. But you know, they're both the correct answer. Nothing else will do. Okay, that's the end of the questions. That's the end of this video. I hope it was useful. I'll see you again soon. Bye bye.